Okay, so I'm going to walk you through how to solve these three types of problems. A bouncing collision, a sticking collision, and an explosion. So the first one's a bouncing collision. The easiest thing to do, make your life a whole bunch easier with all these, is to draw the problem out. Like draw the before. So here's everything before, and here's everything after. Right? If you try to just do it in your calculator, you're going to get confused. Draw it out and separate the before from the after, because the whole idea is that the before momentum and the after momentum have to be equal. Okay? So, another thing to make our lives easier, see how all these point left? This one, and this one, they all point left. I'm going to call this way positive. Even though in the problem it says that this way's, the other way's negative, that way's negative, I'm going to call it positive because it's easier if I have everything positive instead of dealing with a bunch of negative numbers. Okay, so all you do is you solve for all the momentum on the before side, and then you set it equal to all the momentum on the after side. So let's just start over here. Here's car 1, so I'll say m1 times v1, and it's negative because it's going in the negative direction, right? Because I called positive that way. And then I'll say plus, this is car 2, so it's mass of car 2 times velocity of car 2. And that equals car 1, so that's m1 times v1 plus car 2 m2 times v2. Okay, so now let's plug in numbers. So that's 2 times 4, that's 8, so that's negative 8 plus 24 equals 4v1 plus 6. Okay, so let's simplify some more. So 24 minus 8, right, that's 16. So I got 16 equals 4v1 plus 6. Okay, so I want to get v1 by itself, so I subtract 6. Right, let's see if I can. So I can do subtract 6, so that's going to be 10 equals 4v1. So that means that v1 must equal 10 over 4. And so that's going to be like what? 2.2, something like that. I'll just leave it like that because I don't have a calculator. Okay, so that's an elastic, well not an elastic, a bouncing collision. Right? Okay. So here's a sticking collision. So in this case, this is like when you did the ones with the Velcro. So in this case, somebody's going to jump in from a dock into a rowboat, and they're moving, but the rowboat's not moving, and then afterwards they stick together and they move off at the same speed. So again, here's your before, here's your after. Draw the before and the after, and then you can make an equation. Okay, so again, make life easy. See how everything's going this way? I'm going to call that way positive. Makes your life a whole bunch easier. You don't have to always call right positive. Okay, so let's do this. So the rowboat is not moving, right? So the rowboat m1 times v1, that's just 0, right? So the boat is 0. So it doesn't matter. The only momentum in the system before is this person moving. So the mass of the person times the velocity of the person equals, in this case, both these things are together, right? The man is in the boat, so the boat and the man are both moving together. So that means when you do the momentum of the whole thing, it's the total mass of those two things times the velocity of the boat. And there's our equation. So now we can plug in. So the mass of the person is 85, and the velocity is 4.3, and that equals 85 plus 135. That's the total mass of the man in the boat times V2. And that means this is 365.5 equals 220 V2. So now, if I divide 220, 365.5 over 220 equals V2. So that's going to come out to 1.66. So that means they stick together and they move off at a speed of 1.66 meters per second. So that's why we called this one inelastic before, because if you look at the kinetic energy, there's not as much motion in this one. Okay, and so the third type is the easiest type. The third type is the explosion. Explosions are easy. Okay, so same thing. Draw it out. There's an astronaut. If you ever saw Gravity, this is the same thing that was in Gravity. Like, she had a fire extinguisher and she sets off the fire extinguisher. She goes flying backwards, right? Because it's just conservation of momentum. So same thing. Here's my before, and here's my after. Okay, so before, there's an astronaut sitting still, holding this thing. And afterwards, he's going to throw the tank one way and go back the other way. Okay, so same thing. Before equals after. So in this case, the velocity of the person is 0, and the velocity of the tank is 0. So that means the total momentum over here, before, is 0. So this is why explosions are so much easier. Because over here, see how they go opposite directions? It's just going to be the mass of the person minus, the momentum of the person minus the momentum of the object. So if I do algebra, these two things have to have the same momentum, right? Because they're going in opposite directions. This one's going this way, and that one's going that way. So these two momentum vectors have to cancel each other out so that I get a result of 0. So that means that the momentum of the person equals the momentum of the tank. So over here. So 63V equals 10 times 12. So 63V equals 120. So V equals 120 over 63. And that's 1.9 meters per second. Those are the easiest types of problems. If you see something where everything's sitting still at the beginning, that's an explosion. So all you have to do is take the two things that are separating and set their momentum equal to each other and solve. Okay, so those are the three types. You can use those. Try the first two problems in that worksheet.